Hi everyone, and thank you for your attention. My name is Bradley Jenks, and I'm with Hydrotech & Associates, a Toronto-based consulting firm specializing in the hydraulics and energy of urban water systems. I'm also a recent graduate of the University of Toronto, where the water loss management project being presented today was the cornerstone of my thesis. In short, this project is about reducing leakage in the large water distribution systems that lie beneath our cities. A mobile testing unit was developed to facilitate the collection of flow and pressure information in district metered areas, or DMAs. We will touch more on DMAs later in this presentation. Here's a brief overview of the project. In total, there have been 22 DMA sites tested in 8 participating municipalities, ranging from the cities of Greater Sudbury and Ottawa to those around the GTA. The testing program involves the deployment of a mobile testing unit to collect minimum night flows, an indicator of leakage, as well as test the effectiveness of pressure reduction on leakage reduction. From the collected minimum night flow data, performance benchmarking has been developed to objectively evaluate DMA performance. Now, we will first take a look at one of the primary motivations for this research, the intrinsic connection between energy and water supply systems. In fact, this project was made possible through the financial support of the Independent Electricity System Operator of Ontario, or IESO, in recognition of this very connection. Leakage not only represents the wastage of treated water, but also energy and environmental resources, which are required for conveyance through our often vast distribution systems. The pumping power equation, shown here, outlines the conversion of electrical power to water power. As highlighted in blue, higher pumping flow rates from consumption as well as leakage is directly proportional to increased energy requirements. Represented in red is the total lift or head, where pumping needs to overcome the static components, that is the elevation and surface pressures, in addition to the dynamic component associated with hydraulic and frictional losses. Fundamentally, the project employs the methodology of district metered areas, or DMAs. A DMA is simply an isolated area of the water distribution system where the inflow, or inflows, are monitored at the inlet and isolation valves separate the DMA from the rest of the system. Flow is typically monitored through either permanent infrastructure, being the construction of chambers and installation of inline flow meter technologies, or temporary solutions, with insertion or clamp-on ultrasonic meters being most common. As mentioned previously, one way leakage can be evaluated is through the analysis of minimum night flows, which can be monitored over time and compared with other DMA systems to evaluate performance. Here in North America, however, there are common barriers to the implementation of DMAs, which in essence involve the trade-off between installation costs associated with permanent solutions and the data collection issues from low flow detection limitations of temporary metering. The minimum night flow, or period of lowest consumption in the demand profile, which typically occurs between 2 and 4 a.m., is a reliable and predictable indicator of leakage. This is because the minimum night flow, or MNF, represents an instance in the system when consumption is at its lowest, and thereby leakage constitutes the highest fraction of total flow. In short, high minimum night flows suggest high levels of leakage. Of course, there is still actual or legitimate consumption, and we will dissect this a bit further later on in the presentation. There are 2 considerations to note, the first being overnight irrigation, as of course the resulting higher flows are associated with actual build consumption and not leakage. And the second concerns the land use of the DMA. This work focuses on residential DMAs as the diurnal demand profiles are quite consistent and predictable, as shown in the graph on this slide. To help overcome the implementation barriers discussed previously, this project introduces a diagnostic tool or mobile testing unit designed to accurately and affordably measure minimum night flows into temporarily configured DMAs. Quite simply, the mobile unit is composed of a trade van equipped with inline flow metering technology, commensurate with permanent DMA installations, a pressure reducing valve, various fittings and taps for pressure measurements, and piping to convey the supplying flow. As illustrated in the concept sketch here, flow is rerouted across a closed valve through the mobile unit where flow and pressure data are collected, and then back into the temporarily isolated DMA. Connection to the system is made through taps or hydrants on either side of the closed valve. In summary, the approach is affordable by virtue of its mobility, and it is accurate by virtue of the metering technology it is equipped with. The concept builds on earlier experimental work conducted in the City of Ottawa in conjunction with the National Research Council of Canada in the mid-2000s. So here we have a few photographs of the testing setup where flow is conveyed to and from the mobile unit through 2.5-inch or 4-inch fire hoses. The chamber connection is also nicely illustrated in the top two photographs. As a result of the data collection from deploying the mobile unit, performance benchmarking is being developed using the measured minimum night flows and various characteristics of the DMA. For example, the graph on the left shows measured minimum night flow plotted against the number of service connections, and on the right, the ratio of minimum night flow to annualized average bill demand, or in other words, the average day consumption within the DMA. Using these normalized metrics, among others not shown here for the sake of brevity, the performance of any DMA can be assessed relative to its peers. Performance can also be compared with a developed minimum night flow benchmark, which is shown by the dashed line. The minimum night flow benchmark is intended to be an evidence-driven representation of a healthy system with minimal excess leakage. DMAs plotted in the vicinity of the benchmark likely do not warrant further detection efforts. On the other hand, DMAs showing a large departure from the benchmark indicates the presence of potential recoverable leakage, as shown in the red data points. When this amount becomes appreciable, intervention efforts become increasingly valuable. A case study on one DMA showing a large departure from the benchmark is presented later. Now, looking more closely at the development of the minimum night flow benchmarks, which encompass some level of minimum hour consumption, coupled with minimal or a healthy level of leakage. Both elements, of course, have a degree of variability. The rationale used to develop the benchmark displayed previously include the following aspects. First, a statistical analysis or regression of the collected data along the lower trend lines, a literature review of minimum hour residential consumption, a component of the minimum night flow, and to complement and support the literature review findings, an analysis of overnight consumption data from an advanced metered infrastructure or AMI dataset in an Ontario municipality. The AMI analysis provides context to expected overnight flows in Ontario municipalities and will be covered in more depth in the following slides. Reviewing the recorded consumption values in the table to your right, it can be observed that the higher range in values comes from sources in the North American context, and that's between, you can see at the bottom, 2.33 to about 6 liters per customer or household per hour. Here are the analysis results from the AMI dataset, where the objective was to determine an appropriate value for minimum hour consumption in the Ontario context. First, data filtering was performed to primarily discard meters with any apparent errors, low resolution, or weekend consumption. The filtered dataset consisted of approximately 54,000 minimum hour data points over about 2 months in the fall of 2019. Once this was complete, 2 additional threshold filters were applied to exclude extraordinary consumption or data points representing atypical overnight use. The first was informed by the IWA DMA guidance notes, and the second based on the 99th percentile of the current dataset, both of which are represented by the green and purple plots in the chart. In summary, it was concluded that an average minimum hour consumption of 4.5 liters per connection per hour was representative for this Ontario municipality, noting that this is merely a starting point which will be refined as additional data is collected and analyzed. Of course, variability ought to be considered in the noted average consumption value, especially as the dataset used is relatively small. To this end, a statistical bootstrapping analysis was performed. The exercise involved the random sampling with replacement of distributions varying in size n to estimate the statistical properties of the pre-filtered dataset, having a population of about 53,000 entries. Looking at the chart, the y-axis represents the evaluated minimum hour consumption value, and the x-axis the size of the randomly selected sample from the dataset. The sampling was completed 10,000 times for each increment, which resulted in a distribution of outcomes. This is represented by the lower and upper bounds shown in blue, in addition to the average value, which is consistently seen at about 4.5 liters per connection per hour. The results suggest that as the sample size of overnight users increases, the variability in average minimum hour consumption decreases. Naturally, the opposite is true for smaller sample sizes, where a more considerable degree of uncertainty needs to be accounted for, as depicted by the diverging 95% confidence bands. In application, this implies that as DMA size, or the number of connections within the DMA, increases, greater confidence is bestowed on the estimated actual consumption element of the minimum night flow benchmark. For reference, the DMA size range in the testing program is overlaid here in red to show the potential impacts from minimum consumption variability. Switching gears back to the results of the testing program. In one DMA, testing was conducted before, shown in the orange time series, and after, in the blue time series, a repair of a leak. The results were measured to be on the order of 4.5 liters per second, or roughly 140,000 cubic meters per year. This was equivalent to about 100 megawatt hours per year, and the financial savings of close to $430,000 per year. And you can see in the DMA benchmarking plot, the minimum night flow data point was brought down closer to that of its healthier peers. And so to conclude this paper, here are the key takeaways. First, leakage reduction testing program was funded by the Ontario Power Industry, or the Independent Electricity System Operator, where 22 DMA test sites have been completed so far. The development of a cost-effective diagnostic tool, or mobile testing unit, was designed to accurately and reliably measure minimum night flows, an indicator of leakage. From this data, evidence-based benchmarking metrics were developed to objectively characterize and assess DMA performance. And a statistical analysis was conducted of advanced metered infrastructure data, which was used to strengthen the minimum night flow benchmarks. Here are the project partners, ranging from, of course, IESO to the National Research Council, the Ontario Waterworks Association, the University of Toronto, and the participating municipalities where the testing was conducted. All right, thank you for everyone's attention. We appreciate that a lot of ground has been covered in a short time during this presentation, and so we would be delighted to answer any questions. Thank you.